Today we're going to learn about using Simpson's rule.
Simpson's rule is a rule to approximate the area under a graph, and it's named after a guy called Thomas Simpson. Nothing to do with the family from Springfield, but hopefully that's a nice attractive visual to start off with. He was recognised as a mathematician during his day. He was a British mathematician, and he's attributed to having come up with this rule. Whether it was actually him or not is a matter of debate, as it so often is, but certainly he was a prominent mathematician of his day. Get rid of them. Simpson's rule, you can find it in your formula booklet, and this is where we're going. So you might be familiar with the mid-ordinate rule, and this is where it is. It's under the numerical integration section in the formula booklet, and so Simpson's rule is there with it. But what we'll find is Simpson's rule is a more sophisticated way of estimating or approximating the area under the curve. Still not exact as calculus will give you. It's not an exact integration, but it's a much more sophisticated way of finding the area. Now, here we've got two curves, and the curve that we're interested in is the green one, and we can see there's 3 points that are placed on the green curve. That's our function. We're interested in finding the area between our green curve and the x-axis. But what we're able to do is, if we've got 3 points, we can plot a quadratic curve through them. And while our red quadratic isn't exactly the same as the green curve, which is actually a cubic, certainly over those 3 points, it's mighty close. If we zoom in, as we have here, then you can see that I've enlarged the scale a lot there, and I've thinned out the lines. You can see that the lines aren't exactly on each other. So if we find the area under the red curve, it's not going to be exactly the same as the area under the green curve. But like I said, it's an accurate approximation. So with the 3 points, what Simpson's rule does is it uses those 3 points to form 2 strips, and it integrates the quadratic to find the area under the quadratic. So what we're interested in is, for the green curve, and you can see there it's a cubic, is we want to use the limits of 0 and -6 and find the area under our green curve in that range. So how are we going to do that? We've just got 2 points and they're between -6 and -4. So what we do, we actually split it into further pairs of strips. So there's our second pair, blue area, between -2 and -4. And what you notice is the quadratic that we formed on this one, the red curve, is different from this quadratic that's been formed for our second pair of strips. We need another pair as well. And here it is. So what you see is the quadratic here is you just see part of it. It's not obvious it's a quadratic, but here it is. And over this section of the graph between -2 and 0, it is a very close approximation again. So what we're going to do is we're going to integrate the area using this quadratic between -6 and -4. And we're going to integrate between -2 and -4 for this second quadratic, and then for our third quadratic, we can find the area by integrating between -2 and 0. So the way we do this is we consider each quadratic as a general quadratic, and we do it assuming that the midpoint is on the y-axis, and so that the other points, which are the same distance either side, you can see from here, if we picture this point as being on the y-axis, then the distance that our first point is, and the distance our second point is the same either side. So if we call the width of our strip as d, if this is the y-axis, then the x-coordinate of this one will be minus d, and the x-coordinate of this one will be plus d. And so that's why we've got it between those two limits. And we're going to integrate this. What happens next is nothing fancy. There's no numbers there. We've got it in terms of a, b, c, and d. We sub in our values for x, d, and minus d, and that's what we get. That is the area under the quadratic between those 3 points. Now, where we're going to go next is we're going to think about the y values at those 3 points. So our function is ax squared plus bx plus c, same as over here, same as what we integrated. But we're going to find the f, first of all, of minus d, so that's the first point. And there we have it. Then we're going to sub in the f of 0, because it's on the y-axis, so the x value is 0. And then we're going to sub in, or we're going to find the f of d. What's the value? What's our y value when x equals d? And what we're going to do is we're going to try and combine these y values in terms of a, b, c, and d. And can we make it something similar to the area under the curve, which, as you know, is in terms of a, c, and d? So, of course, we can. If we add y0, 4 lots of y1 and y2 together, then this is what we get. Notice that the term in b in y0 is none there, and the term in b in y2, they cancel each other out. So we're left with a term in a, c, and d, which is quite similar to what we're trying to make it equivalent to. Now, if we multiply this line by d by 3, then what we actually get is exactly the same as our integral. So we've got it in terms of our strip width and y values. So we found the area under a curve through the 3 points is the area where the area is under a parabola is given by this equation. So we're after all 3 of those strips, sorry, pairs of strips. We want it between 0 and minus 6. There's our equation for the area under the first parabola for the first pair of strips, the red strips. This is the area, the blue area. So notice instead of y0, y1, and 2, y2, we've got the next set of 3 y values. So the y2 values, they overlap because that value there is the end value for the red area and the first value for the blue area. And then for the green area down here, we've got it in terms of y4, y5, and y6. So what we could do now is we could work out our y values and sub them in and our strip width and find our approximation of the area. But rather than going directly there, we can simplify the formula a bit. You'll notice that all 3 areas have a factor of d by 3 that we can take out. And here's a simplified version of it. We've got 1 lot of y0, we've got 4 lots of y1, but our y2 comes in both on 2 areas. So we've got 2 lots of y2. Similarly, 4 lots of y3 and 2 lots of y4, y5, and by the time we get to the last one, there's just the 1 lot of y6. Nice way of remembering this is like this. We've got the strip width divided by 3, and then the ends, that's the first and the last, we've just got one of them, We got the sum of them though. For the odds, y1, y3, y5, we got 4 lots of each of those. And then for the even values, y2, y4, 2 of them. Note that this only works for an even number of strips. When we're dividing up the area, it's got to be even. They come in pairs. If you're in your exam and you're asked to use the Simpson rule and then decide to divide it into, say, 5 strips, an odd number of strips, I'm afraid you're going to be losing marks straight away. And I said we come back to this. This is the what's in the formula booklet, and there we've got it. We've got a third times the strip width. We've got the ends, and then 4 times the odds, and 2 times the evens. So we've got our formula. Now we just need to work out the strip width and our y values. So first of all, strip width. We can you see by looking at the diagram, since we've got it, that our strip width is 1. For example, our first one goes from -6 to -5, but we don't always have that. So strip width, it's the difference between the limits. Ours is 0 and -6 divided by the number of strips that you want. There we go. Our limits and the number of strips we want. Strip width is indeed 1. Next step, we need the y ordinates, but we need to find the x ordinates first and then calculate the y's. So here's our table. Our first x ordinate is going to be our lower limit, -6. Then we've got 1 strip width to get the next one, and so on until we get to our upper limit. Now we've got our x ordinates, we can work out our y's. We're going to use our function. We can find these exactly, and we can find those for each of our x ordinates. So we've got our y ordinates, we've got our strip width. We can sub in our values and calculate the area. There we are. We've used the Simpson rule to calculate the area under a function. One last thing to look at is how accurate an approximation is this. And so there's the area that we've just worked out. That will be the exact one. And of course, I've chosen this example so that we can do this comparison. And using calculus, we find the area is mighty close to what we found using the Simpson's rule. What's the relative error? That's how we find it. The actual error is the difference between the values, and the true value is what we find from calculus. For that, less than 1% error. And if you want it even more accurate, we can split it into more pairs of strips.